So in this exercise, we have severities that follow a uniform distribution on the interval between 0 and 100. And we have given a frequency distribution in the table. So there are two parts. In the first part, we're going to calculate the twofold convolution over cumulative distribution function. And in the second part, we're going to find the cumulative distribution function over aggregate loss random variable. So I'm going to sketch the situation a bit like this. So so the class was about this individual risk model, but now we're going back to the compound risk model or the collective risk model. So we consider S, which is our aggregate loss. And we can write this as the sum of x1 to xn, where n is itself a random variable. It's the number of individual payments. And in the question, we're given that the frequency distribution is according to the table. So it's this n that follows the frequency distribution as given in the table. Then we also have our xi, like this. So these are our severities, or claim severities. And these xi's are following a uniform distribution in the interval 0 to 100, like this. Now, important, so our x is a uniform random variable between 0 and 100, so it takes values in the interval 0 and 100, so it's a non-negative random variable, like this. Okay. One thing that I need to stress, so we're in this collective risk model, so we know that conditional on n equal to n, or xi's are independent. And actually they are independent and identically distributed because they all follow this, this uniform distribution. So for the first part, I'm gonna move a bit upwards. Okay. Or I'm gonna put another slide that's maybe more easy, like this. Okay. So for the first part, we are asked to calculate our twofold convolution over cumulative distribution function x. So this, okay. So I think you saw this in class already. So in general, if we have our Enfold convolution, which we denote with convolution of f of x, we write it down as f of x star n of a point x. So it is the probability that the sum of n over, in this case, uniformly distributed random variables takes on a value smaller than or equal to x. So like this. Now in class, you saw that based on this, on the fact that you here have these, I'm gonna write this a bit different. So we have n minus 1 to xn. So in class, you saw that based on the fact that you have this sum of n minus 1 over random variables, you build a recursive relation for your Enfold convolution of fx by conditioning on the values that our xn can take. And this recursive relation is as follows. So we have the Enfold convolution, like this. it's equal to the integral from minus infinity to plus infinity over n-1 convolution, like this, evaluated in x minus y times the density function of x evaluated in y times dy. So this was a general formula you derived in class already. Now, what you then did was, okay, we have our x. X is a non-negative random variable. It's a positive random variable. So we can change our boundaries, and because we know that the probability here, the n-1 fold convolution will only take values that are non-zero if x minus y is positive. So we can change our boundaries from 0 to x, since in that case x minus y, where y goes from 0 to x, will be positive. So this was then the general recursive relation that you already saw in class. And on top, you also made a convention that the CDF of a zero-fold convolution, this is equal to 1 if x was larger than or equal to 0, and 0 if x was strictly smaller than 0. So this is what you already derived in class. Now for this exercise, we are asked to calculate the twofold convolution. So if we write the general formula for twofold convolution, say, okay, it's the integral from 0 to x, this over one-fold convolution, evaluated in x minus y, times the density function evaluated in y, like this. So you see that in order to calculate a twofold convolution, we actually need these two parts. So we need this one and this one. So we're going to reflect a bit on both these parts. So we're going to start with this one-fold convolution. Okay. So to calculate this one-fold convolution, we're going to use the recursive relation again. So we have the integral from 0 to x over zero-fold convolution, this, times the density function of x times dy. Okay. Now, a zero-fold convolution is 1 if x is larger than 0, and 0 if x is strictly smaller than 0. So, well, if we look at our boundaries, like this, and we look at x minus y, we see that this will always be larger than or equal to 0, since, of course, our x is also x is larger than or equal to 0, because we're working with this non-negative random variables, right? So these we can actually replace this zero-fold convolution by 1, and we get the integral from 0 to x over density function over uniformly distributed random variable. And then you know that using the definition of a cumulative distribution function, this is actually simply equal to a cumulative distribution function over uniformly distributed random variable evaluated in the point x. So that's for the first part. Then for the second part about the density function of x, well, like this. So we know that x is uniformly distributed. So if you look in the appendix, you will see that this is actually equal to 1 over, well, in general, for a uniform distribution between a and b, it's b minus a. For x in between A and B, and 0 elsewhere. So in our case, with where A is 0 and B is 100, we get 1 over 100 when x is in between 0 and 100, and we get 0 elsewhere, like this. Okay, so this is for the first part, and then for our cumulative distribution function, which we also need, it's actually again using the cumulative distribution function of a uniform distributed random variable, and this is equal to 0 if in general x is strictly smaller than a. It's x minus a divided by b minus a for x in between a and b, and it's 1 if x is strictly larger than b, so like this. So again, in our case on this exercise, we have 0 for x smaller than 0, we have x divided by 100 for x in between 0 and 100, this, and we have 1 for x strictly larger than 100. Okay, so we have our components now to calculate our twofold convolution. Okay, so I'm gonna open a new slide like this. Okay, so I'm gonna write this a bit what we already found. So we have a twofold convolution. So like this, okay. And we found expressions for both the, yeah, this is actually just the cumulative distribution function, this. Okay, so we found an expression for a cumulative distribution function. We found an expression for our density function, so we're ready to go on this integral. Now, an important thing to remember when calculating this twofold convolution is to distinguish different cases, and that's what we're gonna do. So you really have to look at what you need to calculate and yeah, what it means. So I'm gonna first reflect a bit on this twofold convolution, namely that this twofold convolution is based on this sum of two uniformly distributed random variables on the interval 0 to 100. Yeah, so if x1 takes values in between 0 and 100, and x2 takes values in between 0 and 100, then we know that this sum will take values in between 0 and 200, right? So 100 plus 100 is 200. So if you think about the twofold convolution, which is the probability that x1 plus x2 is smaller than or equal to x, this. Okay, what about the case when x is smaller than 0? What will the probability be in that case? Well, we know that our sum will only take values, or will take values in between 0 and 100, 200. So we know that when x is smaller than 0, we know that this probability will be 0. Then the case when x is strictly larger than 200, right? What we'll then know is that our sum will take values in between 0 and 200. So the probability that our sum is smaller than at least 200 is 1, right? Because this will always be the case. So we know that our twofold convolution in that case will be equal to 1. So you see that the situation where we really need to concentrate on is situation when x takes values in between 0 and 200. So that's what we're going to do now in a second step. So what if x is in between 0 and 200? Okay, so we're going to look back at this formula for twofold convolution. Okay, I'm going to take another color like this. Okay, so what we see is we have our boundaries 0 and x. So here is our x. We don't know what the value of x is, but we know it's in between 0 and 200. We have here a density function of our uniformly distributed random variable, and it's evaluated in y, where y takes values going from 0 to x. So y will take values in the interval 0 to x, because these are our integration boundaries. And we know that our density function is the density function of a uniformly distributed random variable in between 0 and 100. So it will only be non-zero in the interval 0 to 100. And x will be in the interval between 0 and 200, right? So you see that in the case where x is in between 0 and 100, right? So we see that our integration boundary in that case will be smaller than or equal to 100. And our y will go in between 0 and x, which is smaller or equal to 100. So then for density function, will just be 1, right? Because we know that it's non-zero in between 0 and 100. So it's not a big problem in that case. But in the case that our x is in between 100 and 200, which is also possible because we know it's in between 0 and 200, but we don't know what value exactly. Well, we see that if this is larger than 100, so it's like this, bounded like this, then we see that our y, well, since it takes values in between 0 and x, it can take values that are larger than 100, and in that case, a density function will take a 0 value. So you see that you need to distinguish between those cases where x takes a value in between 0 and 100, and where x takes a value in between 100 and 200. So we're going to do this in the next step. So in the first case, we're going to consider the case where x is in between 0 and 100. So in that case, okay, we're going to write down the formula for twofold convolution again. This in x, it's the integral from 0 to x over a cumulative distribution function times a density function, like this. Okay, but what do we know about our density function? I'm gonna write it again here. So it's 1 over 100, or it's 0, and it's 1 over 100 in the case that x is in between 0 and 100. So like this. Now, okay, if x in our boundaries of our integral takes on a value in between 0 and 100, then our value y, yeah, which goes in between 0 and x, will always take on values that are between 0 and 100. So what we can do is we can actually replace this density function with 1 over 100 and the value for a density function in case y is in between 0 and 100. So like this. So that is not a problem at all. And then we get the following. Then we need to look at our cumulative distribution function. So which was, I'm gonna write it here again, which was 0 for x minus y is x minus y divided by 100 and 1. So it's x minus y divided by 100 in the case that 0 is smaller than or equal to x minus y, smaller than or equal to 100. Now, well, in which situation are we? Well, we know that y will take on values in between 0 and x, which means that our x minus y will take on values in between yeah, 0 and x is smaller than this 100. So we're actually in a situation where we can use this part of the cumulative distribution function. So it's, if we write this down, so we have the integral from 0 to x of x minus y divided by 100 divided by 100 to the power 2 times dy. Okay, if you solve this integral, you get it's 1 over 100 to the power 2 of x times y minus y squared divided by 2, evaluated from 0 to x, and it's x squared divided by 20,000. So like this. So this is the result for a twofold convolution in the case that if we evaluate our twofold convolution in the value x, and x takes a value in between 0 and 100. This is our expression that we need. Now, for the second part, we're gonna look at the case where x takes values in between 100 and 200, like this. Okay, so I'm gonna write this down again. Okay, so now we know that x is larger than 100. So what we can do is we can split this integral. So we can say it's the integral from 0 to 100. Shorten this a bit. This plus the part that's left, so the part from 100 to x over cumulative distribution times a density function y dy. Okay. Now, what do we know? So if y takes values in between 0 and 100, we know that this is equal to 1 over 100. That's what we've seen before. And we know that if y is larger than 100, so this is the case in the second part, we know that this takes on a value 0. So in fact, actually, we can just remove the second part of the integral and our convolution. Our second-fold convolution in this case is equal to the integral from 0 to 100 of our cumulative distribution function times 1 over 100. So this is the formula that we're going to discuss now. Okay, so well, let's have a look at our cumulative distribution function in this case. I'm going to open a new slide. So we have so this is the integral that we need to solve now. Okay, so let's have a look. Okay, so our x takes a value in between 100 and 200. Our y follows the boundary, so it takes the values in between between 0 and 100, so like this. Okay, this means that x minus y will always be larger than or equal to 0. Okay, then we have a cumulative distribution function evaluated in x minus y. Okay, so x minus y will always be positive. So we consider the case where a cumulative distribution function is equal to this if 0 is smaller than or equal to x minus y is smaller than or equal to 100, and it's 1 if 100 is smaller than or equal to x minus y. Okay, so what we then see is from this first condition, okay, we know that our cumulative distribution function evaluated in x minus y will be equal to x minus y divided by 100 if 0 is smaller than or equal to x minus y is smaller than or equal to 100. So this is the case when we're gonna reform this a bit. So this is the case when, and now I have to think, so it is just gonna do it. So this is minus x smaller than or equal to minus y smaller than or equal to 100 minus x. So this is the case when x is larger than or equal to y is larger than or equal to x minus 100. Okay, but you see x larger than y, x is an element in 100, the interval 100 to 200, but y is bounded from above from this 100, so we're gonna change this boundary to 100 like this. So if y is in between x minus 100 and 100, we see that we can use this part of our cumulative distribution function, namely that it's, if we evaluate it in x minus y, it's equal to x minus y divided by 100. Now, the other part here, so we see that cumulative distribution function is 1 if 100 is smaller than or equal to x minus y. So this is the case when, again, the same thing. So we have 100 minus x is smaller than or equal to minus y, or x minus 100 is larger than or equal to y, and we know that y is bounded from below by 0. So we have the following condition here. So we have this condition, and then we have this condition from before. So we see that in order to calculate this twofold convolution, where x takes values in between 100 and 200, we again need to distinguish two cases in order to know which part of our cumulative distribution function we can use, right? So we're going to split up the integral again. So we have a twofold convolution. This integral from 0 to 100 of our cumulative distribution function, like this. So we're gonna split it up again with the boundaries, with the conditions that we just found. So we have the case from 0 to x minus 100, and in that case, our cumulative distribution function evaluated in x minus y was equal to 1. So we just have this 1 over 100 that is left. And then for the second part, so where y goes between x minus 100 and 100, we know that our cumulative density function, our distribution function, is equal to x minus y divided by 100. We're going to square this for the density function. So we have these two integrals that we now are able to solve. So I'm going to move a bit forwards because I see time is running out. But so these integrals are rather easy to solve, I guess. So I will So it's an exercise that you can do, but I will give you the answer. So if you calculate this, you get an expression. So the first integral, you get x minus 100 divided by 100. And for the second part, you get 1 over 2 times 100 to the power 2 times 200x minus x squared. If you solve this, and then if you want to write this a bit more compact, this is equal to 1 minus 200 minus x to the power 2 divided by 20,000, like this. So this is our expression for the twofold convolution, CDF or twofold convolution. In case that we want to evaluate it in x, and x takes values in between 100 and 200. So I'm gonna wrap things up a bit. So we have our twofold convolution. So what we've seen today is we're going to make a distinction between 4 cases. So we know it's 0. I have to write x. So we know it's 0 when x is smaller than 0. We know it's, now I have to look at it. Okay, so it's x squared divided by 20,000 when 0 is smaller than x is smaller than 100, like this. It's 1 minus 200 minus x to the power 2 divided by 20,000 when x is in between 100 and 200, and it was 1 when x is strictly larger than 200. Okay, so we found our twofold convolution. So you see that it's a very time-consuming process, and if you want to calculate 3-fold, 4-fold, 5-fold convolutions, you will have papers full of calculations. So this is what we wanted to show. But okay, we get a result, and the key thing is to always look at what value does our x take. So make this thing, these different cases also in the assignment, also in other exercises. Okay, now we're not done yet. So there was this second part, but that's now very easy to solve. So we had to find our cumulative distribution function over aggregate loss random variable. Now, also in class, you derived a formula for this based on Enfold convolutions. That is why we calculated our twofold convolution before. So we have our sum, where n goes from 0 to infinity, of the probability that m is equal to n times our Enfold or CDF or Enfold convolution, like this. Now, luckily, if you look back at the table, maybe I can write it. Maybe I can write it down. So it was this. So we have n, and then the probability that n is equal to n. So it was 0, 1, and 2. 0, 6 here, 0, 3 here, and 0, 1 here, like this. So luckily, our n can only take 3 values. So this makes things a bit more easy. So we have the probability that n is equal to 0 times our twofold or zerofold CF, this, plus the probability that n is equal to 1 times our one-fold convolution, plus the probability that n is equal to 2 times our twofold convolution, like this. Okay. Now, to calculate this, we need to again make the same distinctions between the different cases. So, in the first case, we have that where x was where 0 was where x was smaller than 0. So this was our first case. Okay. So our zerofold convolution, it takes a value 1 if x is larger than or equal to 0, it takes a value 0 when x is smaller than 0. So we have 0 for the first part. Then our one-fold convolution, which was our CDF. The CDF takes a value 0 if x is smaller than 0, so we also have 0 on this second part. And then our twofold convolution, we also saw that it was 0 in case x was smaller than 0, so we just have 0 for our CDF over aggregate loss, random variable. Then for the second part, where x was in between 0 and 100, like this, we have our zero-fold convolution, which takes a value 1, so we just get the probability that n is equal to 0, so we get 0.6, like this. Then for the second part, or CDF, this, we know that it takes a value x over 100 in that case, so we get 0.3 times x divided by 100 in that case. And then for the twofold convolution, we know that it is equal to x squared divided by 20,000 in this case, and we have to do it times 0.1 for the probability that n is equal to 2. And for the third case, where x is in between 100 and 200, like this, we have again 0.6 for the first part. We have our CDF for x larger than 100 is 1, so we just have 0.3 for the second part. And then for the third part, twofold convolution, we have to take 0.1 times the expression we found, which was 1 minus 200 minus x to the power 2 divided by 20,000, like this. So this for our third part, and then for the fourth part and the last part, x, so for x larger than 200, like this. Okay, so we again have 0.6 from a zero-fold convolution. Then our CDF will be 1, so we get again plus 0.3 on our second part, and then our last part, the twofold convolution, we saw that it was equal to 1, so we get 0.1 on our third part, and if you sum this up, this is equal to 1. And you find your cumulative distribution function of your aggregate loss.